Okay, so we have a 200-gram point-like object on a frictionless table. So I have the mass of this point-like object is going to be 200 grams or 0.2 kilograms. It is on a frictionless table, so I can ignore any sort of dissipative force, meaning that I will have conservation laws applied here because it's frictionless, so there's no way for me to lose my energy here. And it is connected to a light, inextensible cord. So the fact that it's a light cord means that I can ignore the mass of the cord, and the fact that it's inextensible means that I can ignore any sort of stretching that this cord is going to have. The cord passes through a hole in the table. A beaver is sitting under the table, pulling on the cord to provide tension. The object has an initial speed of 5 meters per second, so an initial velocity of 5 meters per second, and it is moving in a circle with a diameter of 50 centimeters or 0.5 meters. The beaver pulls harder until the object slides in a circle that has a diameter of 20 centimeters. Let's call this the initial diameter. This is the final diameter, which is 0.2 meters. And I need to determine the final speed of this object. So the first thing I need to do is I need to figure out how I want to approach this problem. Uh, the first thing that might throw you off is that it refers to tension. Tension makes us think of forces and generally would guide us toward using a force diagram, but I don't think that's going to be helpful here because forces are equal to mass times some sort of acceleration. In order to go from acceleration to a change in speed, I would need some amount of time, and I don't have any time, so that's not going to be helpful. The next thing that I think of is rotational motion and the conservation of angular momentum. So right away, I know that this is going to be some sort of rotational motion problem. And the reason that I think about the conservation of angular momentum is because whenever we think about the ice skater, right, and the ice skater has their arms out, they are spinning with a certain velocity, and when they bring their arms in, they spin faster. So if I have no friction on this table, nothing to slow me down, nothing to slow this point-like object down, if I change the diameter of the circle, I'm going to be adjusting the speed. So this makes me think that I need to think about angular momentum and more specifically the conservation of angular momentum. So in order to do that, I am going to look at my formula sheet and I'm going to see what formulas I need to be using here. So if I look under rotational motion, none of these forces are going to be helpful for me because I already determined that I didn't want to use forces. You might be able to approach this with centripetal force, but that seems like it would be a very cumbersome way to approach this problem. Rotational kinematics is not going to help me because I don't have acceleration and I don't have time. So let me look at my rotational equilibrium and dynamics problems. Torque could also potentially be helpful, but I think that this angular momentum is going to be the easiest approach to this problem because I know that there's going to be a conservation of angular momentum, and the angular momentum equation is fairly straightforward. So I'm going to come over here and I'm going to write down my conservation of angular momentum, recalling that angular momentum is equal to your moment of inertia times your rotational velocity. So there are two things here that I don't have. I don't have my moment of inertia and I don't have angular velocity. Well, angular velocity is going to be the easiest one to come up with, right? Because we know that we can just use our equations to transform from rotational motion into linear or tangential motion. So if I want to get tangential velocity from angular velocity, I'm going to use this equation here. So I'm going to use that omega is equal to my tangential velocity over my radius. The next thing I need to find is I need to find my moment of inertia for this point-like object moving in a circle. So this can be a little confusing because you might think you need the moment of inertia for the point-like object. But what I actually want in this problem is I want to have the moment of inertia for this disc or hoop-like shape. So I'm going to use the moment of inertia for a hoop, right? Because it's moving in this circular motion, it's drawing out the line of a hoop. I think that I can use my moment of inertia for a hoop in this problem. One other thing that I note, let me do it this way so that you know these are the same R's. So this R and this R are going to be the same. Both of these radiuses refer to the radius of the circle that this point-like object is moving in. So the next thing that I notice is that both of these require radius. I only have diameter, so I need to change the diameter into radius, right? So to get radius from diameter, you just divide by 2. So this will be 0.25 meters, and my final radius is going to be 0.1 meters. And I think that's everything that I need to solve this problem. So I'm going to go ahead and try to work my way through this, right? So the first thing that I want to do is I want to write down my conservation of angular momentum. All right, so that means that my initial angular momentum of the system has to be equal to the final angular momentum of the system. So my initial moment of inertia times my initial angular velocity is going to be equal to the final moment of inertia times the final angular velocity. The next thing I'm going to do is I'm going to replace my I with the mr squared, and I'm going to replace omega with tangential velocity over r. So this means that I will have mr initial squared times velocity initial over r initial, and this will be equal to mr final squared times velocity final divided by my final radius. I'm going to go ahead and distribute this out so that you can see where I cancel things. So this is mr initial squared, velocity initial divided by r initial is equal to mr final squared times velocity final divided by radius final. I have radius initial squared on top and the radius initial on the bottom. So this is just going to be mr initial times velocity initial. And I have the same thing on the other side, but with the final radius. So I can simplify this to the final radius times the final velocity times mass. I also know that my object is not going to be changing mass throughout this process. So I can cancel out the m's, meaning that I get r initial times my initial velocity is equal to my final radius times my final velocity. And I am solving for final velocity here. So I'm going to flip this equation around, right? So that I get the variable that I'm solving for on the left-hand side. So r final is equal to final velocity. The final radius times final velocity is equal to the initial radius times the initial velocity. And then I'm going to divide both sides by the final radius to come up with this equation. So all I need to do now is just plug in my numbers. So my initial radius was 0.25 meters, and this will be divided by my final radius, which is 0.1 meters. And I'm going to multiply that times my initial velocity, which is 5 meters per second. And I will get a final solution of 12.5 meters per second. Now I need to stop and think, does this make sense, right? So if I had an initial radius with a velocity of 5, it was a larger radius, and I pull this thing in, it's moving about a smaller circle that has a smaller radius, but it is going to have a greater velocity. This makes sense because of what we discussed with the ice skater. So if it has a conservation of angular momentum, if you change the radius and you make the radius smaller, then the object is going to have to be rotating faster.